Okay, so let's start over. So what we had last time, we had a unitary action, we had a finite first moment random walk, and we had a sequence of functions which were cocycles. So each one of these is a cocycle, and instead of being harmonic, we said that cocycles harmonicity needs only to be checked around the origin, right? So instead of this being actually the zero vector, it tends to zero as n tends to infinity. Okay? Now what we constructed is, what we did was we took some unitary maps. It doesn't matter what these are exactly for the moment. We found some unitary maps such that we defined Cn tilde to be Un acting on Cn. Now this is a very weird thing. What does this mean? So this means if you plug in a little x, then you have a vector in H, right? So you can act on it with a unitary operator, and for every x you act with that unitary operator to get a new vector. That's what you call Cn tilde of x. Okay, so this is what this notation means. It's a pointwise notation. Okay, unitary operators are not acting on function. Well, you can have them acting on functions from G to L2, but they act pointwise. Okay, so I said L2, but what I meant is the Hilbert space. This is going to be L2 at the end of the day. I mean, every countable Hilbert space is L2 of something. So that's why I might say L2 by accident. Okay, so Cn tilde was defined this way, and then we managed to find we wrote an enumeration of our group, and what we managed to do was to define C of xj for any j, right? This was the limit as n goes to infinity inside some subsequence jk. Jk was an infinite set, so it was the kth refinement of our sequence, right? And this was the limit of the vectors Cn tilde xj, and this holds for every j less than or equal to k. So if you want to converge on j, you have to go to a refinement which is k at least j. Okay? For every fixed point that you want to converge to, you have to go far enough. But there's no one thing that converges for all the points. Let me I think something is okay. No. Now where is it looking? So okay, so okay, so okay, so זהו, תשאיר. אוקיי. So we're not going to be able to do anything. Yeah, maybe move it back now. תעזיב את זה 3 קליקים. זהו, אל תיגע. Okay, so okay, so we had this convergence. Okay, let's okay, and what we wanted to define was did we define the action? We needed to show it's a cocycle, right? So what we did show we showed harmonicity around, well, yeah, harmonicity around 0, right? This is what we showed. Okay.
Now we want to say that it's a cocycle summation, and then we get.
Yeah. Okay. So
the sum being equals to 0, which means it's harmonic at 0.
Yeah, I mean, C of 1 is 0 always for any cocycle. So if you show it's a cocycle, then the average being 0 means that it's harmonic at 0, around the origin, around 1, and then it's harmonic everywhere because of it's a cocycle.
But like
So
for now, it's
so what we showed is that this vector is 0.
yeah.
We showed that this vector is the 0 vector. Okay. Now this construction with the UNs, I want to stress that this construction with the UNs is important. Okay. For example, you could imagine that I take some orthonormal basis BI and I look at CNXJBI. Right? I can look at this inner product. Now these things converge. Why do they converge? Because they're bounded sequences. Just by Cauchy-Schwarz, they're bounded sequences because it's a cocycle, so the norm of this is bounded by the size of xj. Okay? So they converge. So you can take, more and more subsequences converging on all of the j's and all of the i's, right? You could imagine that you do that. And this is good enough to define a limit c. But then I have a problem of proving that that limit is a cocycle. Sorry, the limit will be a cocycle. I have a problem proving, defining what I'm going to do now. You're going to see that these UNs are going to be important. They're twisting things so that they correspond to the correct basis elements. Okay, I need to rotate things so they work nicely with the cocycles. Okay, I tried to think about how to do it without these UNs, but somehow I couldn't. But for us, it's not important because we already did the UNs, so now now we can work with them. Okay, so now I want to define a cocycle. So today, what we're going to do again, we're going to show or find some representation. Okay, representation meaning a homomorphism into U of H, right? Into the unitary operators of H, such that for every x and y, C of xy is C of x plus rho x acting on Cy. Okay?
We said that we already know what rho.
Well, this equation, so that was the next step. This equation tells me what rho has to be, the way rho x. So each one of these is a unitary operator, right? The fact that it's a homomorphism will follow, but each one of these is a unitary operator. And I know what it does to C of y. It has to take it to the difference between these two vectors. Otherwise, I won't get this equation. So I can use that as the defining feature and see, does that define something that is good for me?
This time we don't start with an action and get the cocycle, we start with cocycle and then
we don't even know it's a cocycle, but we start with a function and we want an action that will turn it into a cocycle. We have to use that it's the limit of cocycles in a certain way, of twists of cocycles. These are twists, C tildes are twists of cocycles. Okay, so it's not that every function you can turn into a cocycle, okay? There has to be some, it has to be unitary, there has to be some compatibility. So let's define V to be the span of C of G, right? All the vectors that you get if you apply C to G. This is some subspace of H, right? And the closure. Okay, so first we define. So what are we going to do? We're first going to define it on V. Then we're going to extend it to the closure of V. And then we're going to, on the orthogonal complement, we'll just use the identity, right? That's easy, right? So then we get a unitary map. Okay? So let's first, how do we define it on G? So first, note. Okay, okay, define rho x of Cy, right? So this is an operator acting on a vector. We just define this to be Cxy minus C of x. Okay? And now we want to extend it linearly. Right? So we want to, for any linear combination of these Cy's, right? So any vector in this span, we want to, we want, if I have a sum j equals 1 to m of Cxj, and I want to act on it with rho x, right? So this is a general vector inside this space, and I want to act with rho x. Well, this tells me how you extend it linearly. So I define this to be just the sum j equals 1 to m of c x xj minus c of x. Sorry, I didn't put the coefficients, alpha j's. Alpha j. Okay, alpha j just general coefficient, right? Any vector in this space can be written this way. What is the problem with this definition? Yeah, I mean it's ambiguous because I didn't. Not every vector is not a unique linear combination of the c's. The c's are not at all necessarily linearly independent. Okay, so why is it well defined? We have to check what happens if we have two different representations of the same vector. So if we have cxj's equals to some sum of beta j cxj. Why can I do xj? Well, you know, it's a finite combination. You go up to the m, which is big enough to contain both of the number of vectors that you're using, and then you can put zeros in these coefficients. I didn't say you can. Okay? So if this happens, so assume that we have this situation, right? We have two different representations. We have to show that this answer is the same thing, right? We have to show that this answer is the same thing, okay? So let's write what the answer is. So for some, okay. So we need to show that row x is well defined for a fixed x. Then, you know, it will be for every x, okay? So assume that this happens and fix x in G, right? And then there exists k large enough such that what? Such that this whole sum what do I want to show? I want to show that the difference between row x acting on these two things is 0, right? So I can take okay, so let's do, so it's, okay, alpha j, c x j, row x, minus row x acting on beta j, c x j, right? This is what I need to show is a 0, right? I need to show that this is the 0 vector, okay? Now this thing, what is it? It's exactly, let's put it in the norm. Okay? I want to show it's a 0 vector. It's enough to show it's a 0 norm, right? Now what is this? I can rewrite this vector. Let's use the magic of colors and boards. I can rewrite this vector as what? This says sum, right? By definition, this is sum of alpha j. Then I have c x xj minus cx, right? This one says the same thing with a beta j. But then it's just a linear combination, finite linear combination of vectors. I put them together, right? Okay, so that's the vector that's written inside here. This is what I need to show is 0, right? Okay, to show that it's well defined. Now, this vector, there are finitely many xj's participating, okay, and a fixed x. So if I take k large enough, right, all the vectors x times xj and the vector x itself, all the elements, not vectors, all the elements x times xj and x itself are below some xk, right?
You mean below?
So, okay, so we can look at the set A, which is axjx for j goes from 1 to m. This is a finite set, right? And this is contained in some x1 up to xk for some k. So there exists a k, right? So if I take k large enough, as soon as I have finitely many group elements, I can get convergence, right? I have a good enough sequence for me to get convergence. I can only do finitely many elements of the group at a time, okay? Is that clear why I can do this convergence? Because there are only finitely many group elements participating in this sum, right? So each one of these, this one and this one, are limits of n in a fine enough sequence.
The way we wrote it, isn't it that j is the m?
No, because it's x times xj here. I needed to converge on this one. So this is some xi. That xi, you know, they're finitely many, so I can go big enough. That's all I want, okay? Okay, So I could have phrased it differently. I could have come here and phrased it differently and said that this, for every element in the group, for any finite set of elements in the group, I can find a k for which I have convergence for every element in that set. I can find a converging subsequence for every finite set, right? But you need this finitary statement. We don't have like a uniform convergence for all. Okay, good. So there's this large n of k, so that this thing becomes, if something is the limit, then also the norms converge, right? So that's basic Hilbert space. This just becomes the limit, this is m, n goes to infinity, where it belongs to jk. For this large n of k, all I need is some k, of the norm of what? Of sum j equals 1 to n, to m, of cn xxj minus cnx. Alpha j minus beta j, thank you. Okay? Now let me manipulate this because I don't have so much board. Let me manipulate this just in color. Okay? So what's going on here? These are honest to goodness cocycles. We're guaranteed cocycles, right? So what's written here? X acting on Cn xj. Agreed? That's what's written for this vector. For every n, for every j. Okay?
There is some action of x, right? We don't know.
The action of x is the original action for which we were guaranteed the cocycles. I could have called it some other representation, but this one I took as the basic representation that we have.
I think some, like the limit was inside and you put it outside because it's in
yeah, in Hilbert spaces, if vectors converge, then also their norms converge. That's the norm is a continuous function. Okay, I mean we just do it by triangle and call it. Okay, so okay now. This x is a linear operator, the sum is finite, right? Finite linear combination, so it comes out of the sum. Norm, it disappears, right? It's a unitary action. So what I get here at the end of the day is inside the norm, so I have all of the limit, and inside the norm I just have the sum from alpha j minus beta j. Now what do? This is not good enough for me. I don't know that these converge. What do I know converges? Cn tilde. But I can do Cn tilde. Why can I do Cn tilde? Because Cn is just un minus 1 of Cn tilde, right? And the un minus 1 disappears. It's the same n for all of them. So I can pull it out of the linear sum again and it goes away by the norm. Okay? So now this limit, the norms of converging vectors converge to the correct norm. So this converges to, what this converges to, again, is the norm of the sum of alpha j minus beta j, now I finally remember to put it in the right place, and cxj. But what is this? This by assumption is a zero vector. So this is 0. You go back and forth in convergence, you pull out unitary operators, one time it's the x, one time it's the un minus 1, okay? They disappear because of the norm, and you get 0 norm. So this proves that it's well defined. Now I want you to notice, I could not work if I didn't have the Cn tildes converging. Okay?
The Cn tilde, they convert to the C.
They converge to the C, yes. Now I see that that this is not going all the way to the bottom of the board. Okay. Okay, so this shows that it's well defined. Okay, so rho is well defined. Then we have to also understand why okay, so the next thing we want to do is once we have that rho is well defined, it's well defined on the whole space V, right? Because we show that it extends linearly. We have to show that it can be defined on the limits of vectors of V, right? So if we have now, okay, what was the best way to do it? Yes. So, so if Vn converges to some V, and these come from V, okay? We know how to define rho x of Vn, right? Yeah. So, and let's assume that also Wn from V are converging to the same limit V. Okay? I want to define what rho x of V is, right? What if the, so, because I'm trying to extend rho x to the closure of V, right? My claim is that, okay, so rho x of Vn in norm, what is this? Oh, we didn't say it, but this also showed, this proof also showed that rho x was an isometry. I'll leave it as an exercise. The same thing showed. If you take the norm of this thing, right? Then you pass from here to a limit. The x comes out, the un comes out, you play the game, and in the limit you get, again, you come back to c of y. Okay? So this also proves that rho n, for any v in V, rho n is an isometry. Okay? This proves that fact. So let me put it here. Exercise. Show that for any v in V, rho xv is V. I mean, you do it for any linear combination, which is enough. Okay? Good. So, so this shows that rho x is an isometry. It's a linear map, and it's an isometry already on V. And it takes V to V also because it goes into a linear combination. So now we have a guy in the closure of V, and we approximate it by two different sequences. What I want you to notice is that rho x Vn minus rho x Wn, this is converging to 0 because this is just Vn minus Wn. So this means that these two things, if they converge to the same limit. But also rho x Vn is a Cauchy sequence. And also rho x Wn is a Cauchy sequence. Again, because of the isometry, if you take differences of Vn and Vm, then the rho goes away and you get a Cauchy sequence because we assume that they're converging. Okay, and here I'm using the fact that it's a Hilbert space, not just a vector space. Okay, so since it's a Cauchy sequence, then these things converge, and they have to converge to the same limit because of this. Okay, so rho xv, which we define to be the limit of rho x Vn, is well defined. Right, because we showed it doesn't depend on the choice of vectors. Okay, so this extends naturally to the closure. Okay. Okay. What else do we need to prove about rho? And by the way, the norms are preserved. Okay, so yeah, so I mean, this is the limit of these, which is again this, because here we said it's an isometry, so it becomes an isometry. So in conclusion, let's write down the conclusion. The conclusion, what we have is we have a map. Oh, let me add one more thing. Yeah, okay. So define rho x restricted to the orthogonal complement of the closure of V, right? Just to be the identity. Okay? Now you can always do that in a Hilbert space, right? You can always do that because you can uniquely write every element as the sum of something in V and its orthogonal closure, right? Orthogonal complement. That's why I wanted a closed V, a closed subspace. Okay? So we have a map. So for every x in G, we have a map that goes from the Hilbert space to the Hilbert space. We don't know it's unitary. We know that rho x of V is V for every V in the space. Okay? And we know that for every y, rho x of cy is equal to cxy minus c of x. This is what we know. Okay? And of course, I mean, this is a linear map. Okay, so it's linear. So linear bounded operator, in fact, operator norm is 1, it's an isometry on the Hilbert space. And we want to show that rho is a homomorphism into the unitary operators, right? As soon as I show that it's a homomorphism, it will be unitary because, you see, this tells me that the inverse of rho x, right, is rho x to the minus 1, then I need to show that rho x to the minus 1 is the adjoint. Okay, we'll show that, okay? So, yeah. So why is it a homomorphism? So to check the homomorphism, I'm not writing on the bottom because the camera doesn't get it, so it's right on the top. I think I can basically go one more line. So why is rho homomorphism? What happens if I do rho of xy of c of z? Okay, this will be enough because then I extend linearly, right? If I can show that it's a homomorphism on a basis, right, then I can then I find that it's a homomorphism, right? It is, of course, a homomorphism on the orthogonal complement because that's the identity. So rho of xy of c of z, this is cxyz minus c of xy, right? What is this equal to? Well, this is equal to, you see I have the difference here. So this is rho x acting on the vectors c, y, z, right, minus cy. Why is this? When rho x acts on this, I will get cxyz minus cx. And when rho x acts on this, I get minus cxy plus cx. So the cx's cancel. Okay? And then you see that inside here, I have rho x acting on rho y acting on c of z, right? I mean, this is just the definition. So since this holds for every z, this holds for every linear combination of the c's, so it gets, so this holds for all of v, right? So we get that rho x maps to rho x restricted to v is a homomorphism. And this is enough to say that actually that rho is a representation. I'm not doing all the details, but you can take it from here, right? I mean, it's very easy to see that. Just as functions, rho xy becomes rho x composed with rho y. Okay? Good. So, so it is a representation. Now, why is it unitary? So what do we need to show that it's unitary? We need to show that it preserves inner products, right? So, well, actually what we need to show is that both rho and its inverse, right? Is it enough to show that both rho and its inverse are isometries?
Yes.
Right? So I think this follows because we know that rho is an isometry, right? And rho x to the minus 1 by the homomorphism property is rho x to the minus 1 is also an isometry.
Because you have one side of the inverse, which is the adjoint, but now you have that the adjoint also has a one-sided inverse.
Yeah, right, yeah.
So I think it's
Yeah. So there was an exercise where I told you, I don't remember which side it was, where, well, okay, it's an exercise to prove that if you know this, that if you have a map and its inverse are both isometries, then it's unitary, okay? So this is an exercise to complete.
I think that this is not even an exercise because you know that you have an invertible isometry, it has to be unitary.
Does it?
Yes.
Well, okay, that's the exercise to explain why that's true. So prove, the exercise is to prove if I have an invertible isometry, whose inverse is also an isometry, then prove that it's a unitary map. I mean, I don't think it's difficult. I think it should be easy. Okay. It's some abstract game with Hilbert spaces. I mean, I basically see how to do it. Okay. You could also do it directly on on the C's. Just figure out what's going on, and then you prove that the adjoint of rho x is the inverse of rho x. Just directly on the C's, and then you extend it to any basis of V, and so you get that's true. Okay, so this proves this completes the proof that that we have, right? So we found a unitary now. Now this unitary representation was a weird representation. It was hard to follow because remember we had the UNs in the middle and they kind of pushed the representation. So we get something very weird. But we do have a representation. Okay, I think we take a break now. And I don't know how to fix, maybe try to fix the camera. But...